Okay, so today we'll cover the next, the second symmetric key algorithm, which is AES, which is basically now it's the commonly used symmetric key cryptography algorithm. DS is old, and the death of DS is imminent, so it is coming. But we are just staying compatible with old versions of software. This is why DS is still used. Triple DS is more secure than DS, but it's slow in software. So efficiency, although also is important criteria. This had the competition to find an advanced encryption standard. Okay, so I think they launched it in 1997. They asked cryptographers, programmers, etc., to come up with a new symmetric key algorithm, and basically the requirements were symmetric key block cipher, large key size, so 128, 192, or 256 DS. Remember, what is the key size of DS? 56. So it is quite small. And the block size for DS was what? 64. So here the requirement was a block size of 128 bits. Okay. So desired features: security, performance, simplicity, flexibility, and license. There were 15 serious participations. So they had two conferences, 98, 99. So basically they did a peer review kind of evaluation. At the end they kept 5. So these are the 5. And basically the one that was chosen is the middle one here. By the way, here these are the names of the 2 guys who did it. From the names here, from which country?
India.
India.
Israel?
Huh? Israel?
Yes,
no.
Jewish.
No.
Russian?
Damon. This one maybe is not, but this one, the first name. Think about football players.
Roman?
No.
Spain?
No.
Can you pronounce it?
This is Raymond.
Raymond, okay.
Yeah.
And?
Raymond and Damon. This looks like
Greek.
Netherlands. But Netherlands and Belgium, they're very close. So these are from Belgium. Okay, these 2 guys are from Belgium. Anyway, for me, I would know. I would guess.
What do they mean by licensing?
Licensing. They licensing. It should be. It should have the licensing properties. I mean, software license. So you need to be able to authenticate who is using that version of the software. Okay. Yeah, because when a certain implementation is used by in some software tool, you need to map that implementation to the people who wrote that. Okay. Because here we are discussing the algorithm, okay, how it works, what are the transformations. But another thing is the implementation, okay. And implementation, you should be able to say who implemented what, okay. So this is basically licensing to link implementation to the actual. Link the implementation to who did it, to the author. Okay. Yeah. So the middle one, basically this is pronounced Rainbow. Okay. And basically this is the name of the algorithm, and then it will call it is now known by AES. So AES and Rainbow, they are similar. They mean the same thing. Okay. So. All those 5 shortlisted algorithms were fine in terms of security. So all the algorithms are good enough on security, but Randall is simple and fast. So basically they chose that version, that algorithm because of the efficiency and the simplicity. Okay, this is major criteria. Okay. Yeah. So AES, it became standard in 2001, so it's a recent one. So AES is a non-fistal cipher, so the DES we saw is a fistal, is based on the fistal function. Cipher that encrypts and decrypts data block of 128 bits, so the block size of encryption is 128 bits. In DS, how many rounds? 16. 16. In Randall, we do, or AES, we do either 10, 12, or 14 rounds, depending on the size of the key. Okay, and the key size is not fixed. You have versions with with a key of 128 bits, a version with 192, and a version with 256, and the difference is in the number of rounds. Okay. So yeah, there are 3 versions, 10, 12, and 14 rounds. Each version uses a different key. Okay. But the round key, remember in DES, the round key is, what was the size?
48.
48. So basically from the first 56-bit key, we generate 16 48 bits different keys for every round. Okay, here the size of the key, although even if you use the version with the key at 156 bits, the round key is always 128. Okay. So this is how it works. Basically, we have the number of rounds here. There is a pre-round transformation. Basically, it is pre-round transformation is just adding the key. So basically, mixing the key, and then you have the number of rounds that they vary. So you have here the number of rounds. Yeah. So here, the block. Or the size of the data block that is given as input for AES in every round, we represent it as state. So basically, if you take bits, 8 bits from a byte, so you can represent a byte like in vertical like this, then a word is composed of 4 bytes, which is how many bits?
32.
32 bits. So every word is 32 bits.
Which parts?
Sorry? Sorry?
What? Bits or bytes?
Word.
Or bytes?
These are bytes.
Yeah. 8 bits.
Sorry? These are
Each 8 bits, yeah.
are bytes. Basically, a word is composed of 4 bytes. Here it's a bit confusing. This is a bit, this is a byte.
This is bold, actually.
Yeah.
On bold one.
Maybe. Yeah, this is bold. Yeah. So basically, a word is 32 bits. And it's represented as a matrix. Then, a block is composed of 4 words. So which give you how much? 120. 32 times 4, 120. Okay. So basically, and these 128 bits, the block, we call it the state, and we represent it like this. Okay. So word 0, word 1, word 2, word 3. Okay. So for example, if you have a text like this, okay. Suppose it contains so a little bit less than 128 bits. Okay, just you will fill the remaining bits to 128 by just dummy data, and then you will represent every character in its hexadecimal format, and then you put them in a kind of matrix like this. So basically, you see here 0, 0, 4, 12, 14. This is the first word, then 12, 04, 12, 00, etc. This is how we turn data into a state, okay? Because the state is the input for the output. So once you have the state, you do these transformations. So every round you do these 4 transformations in every round. Okay? So you do sub-byte, you do shift rows, you do mixed columns, and then you add the round key. The only difference, basically, in the before the first round, you do one add round key. Basically, you inject or they mix the key without any. This is a pre-round transformation. Okay, this is so it happens in the before the first round, on round 0 itself. In the in the last round, which is basically if you have 10 rounds. the 10th round, you don't do the third transformation, which is mixed guns. Okay? Mixed guns is not applied for some reason. Now, these are the transfers. So we have the substitution, permutation, mixing, and key add. Okay. So the first transformation, which is substitution, basically this one, subbytes. Okay. So you see here it's easier than DES. In DES sometimes the inputs 32 bits, the output is 48 bits. Expansion, etc. Compression, etc. But here, you know, state as input, state and output, state as input, state and output. All of them are states, so 28 bits, 128 bits for every transformation. So the subbytes, basically, subbytes used at the encryption side, we interpret a byte, we interpret the byte as to exist. It's similar to the S box of DES, the S box. So basically, what you do, this is your state, initial, your input state. You take here we have what?
8.
We have in every cell here. We have a byte, 8 bits. So a byte is composed of 2 hexadecimal words, or the hexadecimal characters, let's say, or values. Okay. So you take the first hexadecimal value, and this will be basically the rows index, the index of the rows. And the second hexadecimal value will be the index in the column. And you take that value and you put it in the output.
How do you know which cell to use?
Sorry?
How do you know which cell to use?
You will apply it on all of them.
No, in the block.
Here?
No, the block.
This one?
Yes. How do you know which one to choose?
No. You don't choose. You will repeat this process for every cell.
Oh. This is the.
This is exam, one exam. But you
the
repeat.
whole data.
Yeah. This is the whole data. So basically, this is the substitution table. But here we have just 6 rows. Normally, this matrix should be what? Should be what by what?
F by F.
Huh? So F, it means
16 by 16.
16 by 16. But we have 6 here.
The
Huh?
second slide.
Next slide, yes. So we have here 16 by 16, and this is the inverse. You will do the inverse on the other side. So I don't know if you have, for example, 3B as input, okay, in your data before substitution, you have 3B. You will go to the index of the row 3 and the B as index of the column. So E2 will be the same position of in the output. Okay. So this is as I told you, very similar to S box in DES. Okay. And of course you need the matrix, and you have the matrix for encryption and an inverse matrix for decryption. They are inverse. Okay. So if you apply the subbyte or the substitution with the subbyte matrix, and then you start from that output and you apply the inverse or the substitution with the inverse subbyte matrix, you will get the same input. They are inverse. Okay, so this is the first transformation, which is subbytes. Now, the second transformation is shift rows. From that state, you will apply shift rows, and it's basically shifting the rows. So here, you will take every row of the state, and you will apply a shift left. So you will shift to the left. Okay, shift to the left, but here it's not really shift, because when we shift, if the bit at the most left side, what will happen with that? It will be lost. But here it is meaning rotation. It is rotate. Basically, you rotate 0. When you rotate 0 with 0, it means what? We didn't do anything. Just we kept the row as is. For the row 1, we do rotation or shift of 1 byte, and row 2, 2 bytes, row 3, 3 bytes. An example here. Yeah, so this is an example. So basically, this for the first row, when you do the shift row, there is no shifting. The second row, this is the input. Basically, when you do a rotation to the left, F2 will become here, and this F2 will come this way. Okay, so you obtain this. Okay. The third rule, you do it 2 times. So basically, the 7D will be at the last side, last cell here, and the 2C9 will be anyway. So this is typical left rotation.
So it's not permutation?
This is rotation. We are not permuting anything. Yeah, you can see it. Yeah, it's a permutation. So you are replacing the cells. Yes, you can see. You can say it's a permutation. Yeah. Third transformation is the mixed columns. So in the mixed columns, basically this is where we do the actual mixing. So here it takes you need a constant matrix, and you will multiply the state with that matrix. Okay. So basically, if you have your data here are not A. This is an example of computing just one column of the output. So basically, the input contains here.
X, Y, Z, T.
Yeah, X, Y. Yeah, X, Y, Z. So here we are doing it just for the first column, and you should repeat that for all the other columns. So what you do to compute the first value of that output column, of the first output column, what you do? A times X plus B times Y plus C times Z. So basically, A times X, B times Y, C times Z, D times T, and you put it here. The result is one value. Yeah, matrix multiplication. Then for the second value here, you will do it with the second row. So E times X, F times Y, G times Z, H times D, etc. Okay, and you do the result. So you repeat it. Basically, you need to repeat it for every cell of the output. Every one of the how many of them?
4 times.
16 cells, right? The state. In the state you have 16 positions. 4 by 4.
4 by 4.
Yeah. So you need that to repeat that computation for every cell of the output
For
state.
every byte or for every.
For every byte, because the cell is a byte. So this is the example of one transformation of a mixed columns. Okay. So again, this is the same representation of the mixed column. Inverse mixed columns does the opposite, and then adding the round key is just a matter of adding the values, basically. Not even zoning; it's adding the values. So you take the key. Here. The key also, what's the size of the key in every round?
128.
128. So basically you would be taking the first, the current state with the current key, and then you add them column by column. Take the first column, add it with the first column of the key. Take the second column, add it with the second column of the key. That's it. Even if you are not confused, if you are confused, I will be showing you. Let's show you this. I'm showing you an animation. It's nice. There's some guy from I think Chile who did a nice transformation for a nice animation of AES. So this will help you see things clear. We will cover the key generation from this animation. So basically, result. So as input, it takes some plain text, the cipher key, and it will generate the cipher text. Okay. So basically, what you do, you will for every round you need or not for every round, you split your data into blocks of 128 bits. You represent the data as a state like this, and of course you need a key for that. So here we are. Yes.
From where do we bring the key?
Key is generated random. For symmetric key cryptography, we said in the cryptography introduction, the key is generated randomly. It's like random bytes, random bits. Okay. Asymmetric key cryptography, the key should be very well generated using a certain process. But in symmetric key cryptography, the key is just random. Okay. So as input to AES, you need the state or the block of the data you want to encrypt, and the key. Here the key is of size 128. So you use that cipher key to generate several keys for every round, and you use the state for encryption. So how it goes? So this is the process. Basically, as I told you, the initial round, the pre-round transformation, all what you need to do is to add the round key. So add the column by column. Okay. First column of the state with the first column of the key.
Oh, I see.
That's it. And then second column of the state with the second column of the key. Then you do in total, when in the 128-bit version of AES, how many rounds you can do? 10. So you do 9 main rounds, and the final rounds. Why we're a little bit make it different? Why we do that?
There's no mix.
It is missing this step. Only the last round. It's missing this mixed column steps. Now, so this is how it goes. It will do those rounds, around 4, 5, 6, 7, 8, 9. Then go to the last one, and it will give you the ciphertext. Okay. So these transformations, again, to review, sub-bytes. Sub-bytes, basically, you take every cell. How are we gonna do it here?
Row 1, column 9.
Yeah, row 1, column 9, and you take that D4, and this will be the output.
Yes.
Okay. Now you repeat that for all the cells. Okay. So this is the S box, the first transformation. Okay. Second transformation is the shift rows. So basically, for the first row, we don't do anything. Just
we shift by
the second one we shift by 1 or rotate by 1. Okay. So we rotate by third row we rotate it by 2, and third and the last one we rotate by 3. Okay. And this is your out. Okay. Now the last the mixed columns. The mixed columns here you need the matrix. Okay. So you're gonna build up the output state column by column. So basically, what you're gonna do here, basically, we are doing D4
by 2
times 2 plus BF
times 3.
times 3 plus 5D times 1 plus 30 times 1, it will give you 4. Yes.
From where do we bring the matrix?
They are known. They are known. All those methods, the S boxes, the value inside the S boxes, the same thing. They are known. Again, this is the Kirchhoff principle. The system is known. The algorithm is known. All these metrics are available. If you go to the documentation of AES, you'll find them all of them. I think these are the metrics used in the standard.
This is module 128.
Sorry?
Operations are done in module 128.
I guess, yeah, you need the result in hexadecimal. You need the byte at the end of the day. Okay, you repeat that for every column. Okay. So see, row shifting. This is a transformation on the rows, and mixed columns. This is transformation on the columns. Okay. See. So add round key. This is the step where we add the key to the state. Okay. So again, this is very simple. So suppose this is the round key. So basically, you take the first column of the data, the first column of the key, and then you add them, and you get the result. Okay. You repeat it for all the columns.
Isn't this the first initial step as well?
The same thing. Yeah, the same transformation.
Excuse me, sir.
Yes.
Is it addition or XOR?
They carry out XOR.
Is it?
It is XOR because it is addition, but the carry out is
Yeah.
negative.
So it's same thing. It is the same thing. Okay. This is why we loaded plus. Okay. Now the key generation. The key generation, again, from a certain. No, this is not yet the key generation. This is how you do the rounds. So basically, this is just an example. Okay, you start by the first state. Okay, then in the first pre-round transformation, all what you need to do is to add it with the key. Okay, so you obtain this state. Okay, so start of the round. Then you do substitution or subbytes, you obtain this. Then shift rows, you obtain this. Mix columns, you obtain this. And then add it with the round key, you will obtain this. Okay, no, this is the round key.
Yes.
You will obtain the state which will come here. Okay.
But the round key has changed.
Yeah, of course.
Okay.
Because you need a different round key for every round.
Oh, yeah.
This is why we call it round key. How we generate the round key, we're gonna cover it right now. Okay. So you repeat that for every round. Okay. So this will stay for like 9 rounds. The last one, you see, the last step is empty because we don't do mixed guns. Okay. And we get the output. Okay. And now how the key is generated from the first cipher key. So you take that cipher key, and then you have a constant matrix here. So this is known also. So what you do, to generate the first column of the first key. Okay, first column of the first key, because in all the round keys, these are the different. This is a round key for or the key for round 1. This is the key for round 2. The first column of every key is quite special to generate it. Okay, the others are easy. Okay, so basically, for the first column of the first key, we do first rotation on of course this previous column, this one. Okay, this previous column. Okay, we do rotation. Then we do sub-byte transformation. Okay, for all the 4 bytes. Okay, we repeat that, and then we add it with the first column of the cipher key or of the previous key, the previous one. Okay, and the matrix here, normally it is this one.
The first one.
This is here on 4.
Yeah,
Yeah, it is mixed here. I think.
This is the fourth thing.
Yeah, the 4.
Yeah, Arcon 4.
This one. On 4 because it says 4. Okay.
He took the first and put it here.
Hmm?
Look, can you go back? Because he took the first, I think, and put it here.
First one. You took it.
Yes, I think. Not sure.
Anyway, basically you go to this constant matrix and you take the column at index 4. That's what it is. Okay. Then you add them all and you obtain that first column. You put it there. Now for all the others, what you do, you just take the second column here with and you add it with the main first column of the key, and normally you obtain the value, put it there. Okay. Same thing for the others. You take the third column, you add it with the previous one. So here basically you add it with the previous one.
Previous other.
Yes, with the previous one. You obtain that value, put it there. Yeah, that's it. So basically, this is what you do, and then for the next round key, you repeat that same process. Rotate, then sub-bytes, then take the previous the first column of the previous key, and you add them with the Arcon 8 here.
So each first block from each key, round key, I will do the same thing.
Yeah. So you repeat that same process for every round key. Okay.
So
Yes.
how to choose the output?
Same thing. It's constant. It's known.
No, which column of the output?
It isn't there. It isn't there.
Ah.
So it will tell you at every round key which one you choose.
4, 8.
Yes. Yeah. So I think that's it. So you will generate those all the keys.
Excuse me.
Yes.
Are we expected to perform this in
You need to understand the transformations. The transformation. Okay, sub-bytes, you need to do how to do it. Okay, you need to know how to do it. Mixed columns, you need to know how to do it. what else? Shift rows. You need to know how to do it. But you don't need to memorize. I will give you everything, but I will tell you. Okay, if this is the input and this is the key, what is the output? If you need a constant matrix, I will give you that. Okay, but you need to understand the transformation. Okay.
Could you upload this, please?
Yeah, so I'll upload it. Yeah, so basically there's a couple of other things here in the slides. Yeah, all this. So AES was designed after DES. Most of the known attacks on DES were already tested on AES, so it is secure against the attack on DES. AES is definitely more secure than DES due to the larger size key. It's here. What it says it's significantly more secure than DES. So the AES can be implemented in software, hardware, and firmware. The implementation can use stable lookup process. So here, one of the advantages when you represent data as states, you can implement it in so many different ways, and it is very efficient. Okay. So that I can easily implement it using cheap processors and the minimum amount of memory. Yeah, so that's it for that. And chapter 7 for the book.